Are you guys here? Hello?
Hello, yes.
Yes, okay. Okay, so let's start. So, today's session will be on the topic of basis, dimension, rank, and nullity theorem. Okay, so let's start. So, the first topic is linear independence. Is it visible?
Yes, it is visible.
Yeah. One thing I want to request you guys, please respond quickly, okay? Then it will be very easy for me, okay? Otherwise, it will not complete within that time limit. Okay, so if if set S, that is V1, V2, V3 and Vn is a non empty set of vectors then the vector equation k1 v1 plus k2 v2 plus k3 v3 plus kn vn equal to 0 has has only one solution, k1 equal to k2 equal to k3 dot 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 equal to kn equal to 0, then set S is called linearly independent set. Okay, otherwise it is called what? Linearly dependent set. Okay, is it fine? Is it fine?
Yeah, fine, sir.
Yeah,
Yeah,
okay.
yeah, fine, sir.
Okay, so do I need to explain this or is it fine?
One more, sir. Please explain. Please explain me one more, sir,
Yeah,
if you don't mind.
yeah. What I'm trying to say is, suppose there is a set, okay, and in that set there are n vectors. Those are v of v1, v2, v3, and dot 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 vn. And the thing is, if we can write it in the form of k1 v1, k2 v2, dot 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 equal to 0, where k1 k2 k3 are scalars, and after solving this equation, if we get only one solution like this, I mean k1 equal to k2 k3 dot dot equal to 0, then this set is called linearly independent set. And if you are getting other than this solution, then this set is called what? Linearly dependent set. So that is the theorem. Is it fine now?
Yeah, fine, sir.
Yeah, okay. So let's take an example. Suppose we have V1 equal to 2 minus 1 0 3, V2 equal to 1 2 5 minus 1, V3 equal to 7 minus 1 5 and 8. Then we have to check whether check the set S equal to V1, V2, V3 are, I mean is, because it is a set, is linearly dependent. Can you check it?
Yeah, sir.
Yeah, please check it. I'll give you 1 minute. Okay. So to check whether this set is linearly independent or not, we have to do one thing, like we have to write in this form: k1 v1 k2 v2 plus k3 v3 equal to 0. Okay, so since k1 k2 k3 are scalars, so we can write it like this. Okay, now can we write it like this form also? Can you write it like this? Tell me.
Yeah, yes, sir.
There is -1.
Okay, where 2 minus 1 0 3 1 2 5 minus 1. Okay, fine. Okay, okay, now I have to find k1 k2 and k3. So the first thing we have to do is, it is a kind of ax equal to 0, right? It is a homogeneous system of equation. Homogeneous system of equation. So the thing is, if we get a trivial solution here, what I'm trying to say, if we get k1 equal to k2 equal to k3 equal to 0, which means that what, here we are about to get trivial solution. If we are not get trivial solution, which means that the system is linearly dependent. Is it fine?
Yeah, fine, sir.
Yeah, so first I will convert it into reduced or row echelon form only. Okay, so let's do that. So the first thing is 2 1 7, and I will use row reduced echelon form. So the first I will multiply this row by 2 times and subtract this, so we will get 0 5 5. Similarly, this row will be as it is, and the fourth row will be 0 5 and 5, right? And this will be k1 k2 k3 equal to 0 0 0. Okay, now subtract this row by this row. So what we will get? I will get 2 1 7 0 5 5 0 0 0 0 0 0. Okay, and this will be k1 k2 k3 equal to 0 0 0. Okay, now the first row will be what? 2k1 plus k2 plus 7k3 equal to 0, and the second row will be what? 5k2 plus 5k3 equal to 0. From this you can take k3 equal to t from this equation. Okay, then what will be k2? K2 will be minus t. Okay, then you can see that what will be that then k1 will be what? After putting k1 will be 1 by 2, and that will be minus k2 minus 7 k3, that will be 1 by 2, k2 will be minus t minus 7t. Okay, and this will be minus 3t. Then you can see that the solution will be k1 k2 and k3 will be t times minus 3 minus 1, and that will be 1. So you can see that it is a non-trivial solution. You can say that you can put the t equal to 0. That is also a part of the solution, but the thing is that is not only the solution. What was the situation of this definition? You can see that only one solution. Okay, but here you can see that we are getting not that solution, we are getting many more solution, which means that the system is linearly dependent. Okay, is it fine?
Yeah, fine, sir. If you don't mind, last step, please explain me, sir.
This one.
No, sir.
Okay, this
Please
one.
scroll
Okay,
to
so
up.
yeah, so we can write it. You can see that k1 equal to minus 3t, right? K2 equal to minus t and k3 equal to t. So you can see that t is a common. So we can take outside and we can get minus 3, minus 1 and 1. Okay?
Yeah, fine, sir.
Yeah. So you can also take one more example and you have to solve this. Suppose you have the system S equal to set of 1 minus x, 5 plus 3x minus 2x square, 1 plus 3x minus x square, and check whether the system is linearly dependent or not. Solve it. What about it? The first one, dependent or independent? Okay, let's solve this. So what we have to do is we have to write it like this: c1 1 minus x plus c2 5 plus 3x minus 2x square plus c3 1 plus 3x minus x square equal to 0, right? So now I will take common, so that will be c1 1 plus 5 plus 3, right? Yes, plus c2, not like this. I will suggest to do like this. Here the thing is x square and constant 1 are basis. Okay, basis I will talk about it, but the thing is here I can write like this. You can see that the first one is in the form of 1, okay, plus minus 1x plus 0 x square, okay, and the second one is what, 5 plus 3 into x minus 2 x square, and the third one is like this only. Okay, so when you write like this, then you can see that I can also write 1 minus 1 0, the first one, and the second one is what, 5 3 minus 2, and the third one was what, 1 3 minus 1. Now I have to solve this one, c1 c2 and c3 equal to 0. Will I get the solution for this? Will I get the solution of trivial or non-trivial solution? Tell me. Is it fine what I am trying to write here?
Yeah, fine, sir.
Yeah. So find at what condition we are getting this 0 0 0. What is the solution for C1, C2 and C3? So here you can check that if C1 equal to 3, C2 equal to -1 and C3 equal to 2, then the system here, the system AC equal to 0 will be satisfied, which means that what? S is linearly dependent. Is it fine?
Yeah, fine. Please explain me last step, sir. That C1, C2, C3 values.
Yeah, you can check that. Anyhow, you will get infinite number of solution here. But I'm just checking that if you check C1 equal to 3, C2 equal to -1, I want to say that if you get only one, if anyhow you get one solution at least, such that the equation satisfies, what does it mean? Which means that the system S is linearly dependent, because here you are not getting trivial solution. So that's what I'm asking. I'm just putting C1 equal to 3, C2 equal to -1, and I get C3 equal to 2, which means that I am getting non-zero solution, which means that system is linearly dependent. The thing is, I have to get only one trivial solution, only one non-trivial solution. If I get that, which means that the system is linearly dependent. Is it fine?
Yeah, fine, sir.
Yeah. What about this? You have to just see it and just tell me what is the answer.
Independent.
Yes. Okay. Linearly independent. Now let's move to the another theorem. A set S with one second. Okay. A set S with two or more vector if first, oh sorry, is linearly dependent if and only if at least one of the vectors in S is expressible as a linear combination. Is it fine? Just tell me, is it true or false? True or false? Linear combination, if you are not getting it. What it is saying is, suppose you have the set S, okay, that is V1, V2, Vn, and what it is saying
Sir,
is,
if you don't mind,
yes, what?
if you don't mind, please explain me that first step, a set S with two or more after.
Two or more vector. Want to explain?
Okay, sir.
You want to get explanation, or you're not getting the writing?
I didn't understand writing, sir. That's why I asking.
Yeah, okay. Now it is fine. What I'm saying is,
Yeah,
suppose,
fine.
suppose you have the set S, that consists of the number of vectors v1, v2, v3 and vn. What it is saying is the set S will be called linearly dependent if and only if one of the vectors, at least one of the vectors, can be expressed as a linear combination of others. So which means that suppose you can write rth vector. Suppose you can write rth vector as a linear combination of others vectors c1 v1, c2 v2, dot 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 cn vn. Okay, and in between that vr is not here. Okay, now rearrange it. If you rearrange it, you will get c1 c2 v2 plus, in between that there will be one number, that is minus 1 times vr plus cn vn equal to 0, right? Then you can see that at worst situation maybe c1 c2 dot dot cn will be 0, but at least one index, that is cr, that is non-zero, which means that what, this system is linearly dependent. So that's why if at least one of the vector can be expressed as the linear combination of others, then that system will be called what, linearly dependent set. Fine.
Sir, could you please explain me that linear differentiation, linear differentiation if after.
This is called a linearly dependent. What I am writing here is LD means linearly dependent.
Yeah, because of I'm writing, that's only I didn't understand.
If means if I am writing I double F, which means that if and only if. Okay, and linearly independent means ILI means linearly independent. Okay.
Okay, sir.
Yes.
So this is a linear configuration or the
Linear combination.
combination.
Yes. Fine. Any question
Sir,
here?
if after that,
If at least one of the vectors,
at least one.
at least one of the vectors in S is expressible, I will just suggest that just listen. Okay, you can get all this. I have already
Okay.
shared the OneNote, so you can also note that from there.
Okay.
Okay, just listen and try to understand what I'm trying to say. Okay.
Yeah, okay, sir.
Yeah, you can note it later, otherwise it will take so much time. Okay, fine.
Yeah. Okay. Fine,
Okay,
sir. Thank you,
yeah,
sir.
yeah. Okay, now another situation is a finite set of vectors that contains the zero vector. The zero vector is linearly dependent. Is it fine? Just
Yeah,
tell me
fine, sir.
it's true or false. I'm trying to say, suppose you have the set such that v1, v2 and in between, suppose you have one other vector 0. Then this set will always be a linearly dependent. Why? Because suppose if you want to write rth vector, and that is a combination of like this c1 v1, c2 v2, dot dot dot, in between, suppose you have the vector 0 and that coefficient is something like k, and dot 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 cn vn, then you can see that there is not necessary that k will be 0, which means that you can also set k as a non-zero scalar number. What does it mean? Which means that VR can be expressed as a linear combination of all those, which means that that system will always be a linearly dependent. Okay, fine.
Yeah, fine, sir.
Yeah, okay. Now I want to ask some questions. Suppose we have two-dimensional or three-dimensional space, and Cartesian coordinates are like this. So that is x-axis, y-axis, and z-axis. And suppose we have a vector v1 and another vector v2 is exactly lying on it. So just tell me the set v1 and v2 are linearly dependent or independent?
Dependent, sir.
Good. Okay.
Dependent.
Yes. Now take another situation. Which means that what? Here v1 is directly a scalar multiple of v2. You can see that I can write v1 as a k times v2, right? What does it mean? We can write v1 minus k, or you can also write minus k times v2 equal to 0. Then you can see that here k is non-zero number, or you can see, if you want to put k as 0, then you can see that here it is a non-zero. What does it mean? Which means that C1 is not equal to 0, and C2 you can put any kind of a scalar, or you can put 0. What does it mean? Which means that there is no, this kind of solution is non-trivial solution, which means that the system is linearly dependent. Okay, now you can take another situation, x, y, and z. Okay, and v1 vector is like this and v2 vector is like this. Now tell me, this system is what? Linearly dependent or independent?
Independent, sir.
Independent.
Dependent.
Think.
It is dependent.
What?
Dependent.
Dependent. It is linearly independent, because these two vectors are not lying on each other. What does it mean? Which means that we cannot express v1 as a scalar multiple or combination of v2. That's why this set is linearly independent. Fine? You cannot write.
Okay, sir.
So if two vectors are, if one vector is rotated to an angle, then can they be linear dependent?
Yeah, okay, rotate it. If you rotate it, the vector has changed. Linearly dependent means what? If I am trying to explain in two-dimensional or three-dimensional, and if you want to take just two vectors, then for that system, linearly dependent is nothing but those two vectors must be either parallel or anti-parallel. There is no such extra combination will exist. If you take, suppose if you have a vector v1, then the vector v2 cannot be expressed as a scalar multiple of v1. Never. If this is a linearly independent, then you can also say that e1 vector, that is e1 equal to 1 0 0, and e2 vector, that is 0 1 0, then you can say that these two are linearly dependent. Can e1 can be expressed as in the terms of e2? Never. So that's why there will be a situation, but that we'll also discuss. Okay, now take an example of R3. Now I'm talking about three-dimensional space, and we have an axis, x-axis, y-axis, and z-axis, and we have a plane. And in that plane there is a vector v1, vector v2, and vector v3. Can you tell me the set v1, v2, v3 are linearly dependent? Is it linearly dependent or independent? I have already talked about it very earlier lectures.
Screen is freeze, sir. I'm not able to see that. What you are writing.
What you are not able to see? This one is the v1 vector, v2 vector, v3 vector, and all those vectors are lying in this plane only. Now I want to ask, the set v1 v2 v3 is linearly dependent or independent? So that is the question only.
Independent, sir.
No, you are not trying to get it. This system is linearly dependent.
Dependent. Okay.
Yes, because this is the R3 space.
Yeah, 3D. Okay.
Now suppose we have another system, and the situation is like this only. This is x-axis, y-axis, and z-axis. v1 is like this, v2 is like this, but v3 is out of the plane. Now this set is linearly dependent or independent?
Independent, sir.
Yeah, this one is the linearly independent. Okay.
Yeah.
Yeah. Okay. So
So-
you can see that. What? Tell me.
If those two vectors are if the v3 is the cross product of v2 and v, then will it be linear dependent?
If v3 is a cross product,
Yes, sir.
then what does it mean? Cross product doesn't mean that will be linearly combination of these two. Cross product is a different thing. E3, the vector E3 is the cross product of E1 and E2, but E3 cannot be expressed as the linear combination of E1 and E2. E3 vector or cross product will always be out of the plane. Okay?
Yes, sir.
Yes. So now there is another theorem. Let set v1, v2, vr be a set of vectors. Set of vectors in n-dimensional space. Okay, if r is greater than n, then S is linearly dependent. Is it true or false? Apply your intuitions and think about it. First, simplify this. Suppose we have three-dimensional space, okay, and we already talked about that. If three vectors are such that two vectors are in the plane and third vector is out of the plane, which means that those systems are linearly independent. Now you have an extra vectors. You have an extra vector that will always be the linear combination of those three, which means that what? That system will always be linearly dependent. So here you can see that if those vectors v1, v2, v3, vr in n-dimensional space, and if the number of vectors are greater than the dimension, which means that what? You will have always a linear combination. You can always write one vector in the form of another vectors. So that's why this system will always be linearly dependent. Is it fine?
So, but the extra vector can be like the vector that is outside of that plane, like similar to the previous one.
So that's what I'm saying, na? That's what I'm saying. Suppose you have a three-dimensional space, okay? Suppose you have a three-dimensional space. Now you have four vectors, okay? Suppose you have four vectors. What I'm trying to say is those four vectors will always be linearly dependent. Are you getting what I'm trying to say? Here here you can see that if you have just two vectors, then those two vectors will always be linearly dependent if those two are not parallel. So which means that for three-dimensional space, to get the linearly independent, we require exactly three number of independent vectors to constrain that space, three-dimensional space. But if you have more than three, then what does it mean? Which means that now that space is completely what? You can write any combination of any vectors. So that's why those system will be linearly dependent if we have more vectors than the dimension of the space. The thing is, I can also prove this, but the problem is I don't have much time to prove all those.
Okay, sir.
Okay, are you getting what I'm trying to say? I'm trying to say, suppose you have three-dimensional space, okay, and vectors are like this: v1, v2, v3. Okay, now you have extra vector v4. Now this system will always be linearly dependent because you have an extra vector that is more than the number of dimension of the space, and that system will always be linearly dependent. You can check it. Now suppose I'm taking the example of our Cartesian system: 1 0 0 0 1 0. Can you just tell me these two are linearly dependent or independent? These two are, if you have the
Independent.
dependent or independent?
Independent.
Independent. Now I have third vector 0 0 1. Now tell me, these three are independent or dependent?
Independent.
Independent. Okay, now I have another vector that is
Hows are they linear independent?
these three.
Okay.
You are late. I have already explained why.
Sorry, sir.
Okay, you can check that. I have already discussed that. You will get always C1 equal to C2 equal to 0. Okay, so now you can see that I have already completed the number of dimension that is exactly equal to the number of vectors. Now I have fourth vector. Now this system is linearly dependent because you can always write 2 4 6 as 2 times of 1 0 0 plus 4 times of 0 1 0 and plus 6 times of 0 0 1, because this one is extra. Or you can also say that this one is also extra, or you can also say that this one is also extra. The thing is, whatever after these three or any kind of, or you can say that after these three, or you can only, I want to say, if you select any three and after that just add on, and those extra vector will always be dependent. Now it's fine.
Fine, sir.
Yes, sir.
Yeah. Okay. Whatever till now we have discussed, those are always we are thinking about the vectors. What if we have some kind of functions? Suppose if the functions f1, f2, fn have n minus 1 continuous derivative, or you can say that n minus 1 th differentiable, okay, derivative on the interval minus infinity to infinity, and if the Wronskian, have you heard about the word Wronskian?
No, sir.
I will talk about it in differential equation. And if the Wronskian of these functions is not 0, then the function form linearly independent set of functions. And here Wronskian means determinant of f1, f2, f3, fn, and the second row is derivative of f1, derivative of f2, derivative of f3, derivative of fn, first derivative, and the third row is second derivative. Now you will think that this is not in our syllabus, but it is in your syllabus. And n minus 1th derivative. Now the thing is, it is saying if you have the set of functions f1, f2, f3 and fn, okay, now you want to check whether these functions are linearly set of functions or not. So you have to do one thing, you have to just check the Wronskian, and that Wronskian is nothing but the determinant of these functions like this. The first row is all functions, the second row is first derivative, third row is second derivative, which means that what, if you have n functions, then if it is a determinant, then it must be a square matrix, right? So to have this square matrix, then these columns has also be the same number of the number of rows, which means that the maximum number of derivative it should be, that is n minus 1. Okay, so let's take an example. Suppose you have an example f1 equal to x, f2 equal to sin x. Now someone is asking whether the set x and sin x is linearly dependent or not. Check it. So what will I do? I will write Wronskian, and the first row is what, x and sin x, and second row is the derivative of this, that is 1, the derivative of this, that is cos x. Now what is the determinant? That is x cos x minus sin x, and you can see that this is not 0. So which means that what, this system is linearly independent. Okay, now GATE has also asked similar question. The function was like this, f1 equal to cos 2x, f2 equal to cos square x, and f3 equal to sin square x, and they have asked whether the system S f1, f2 and f3 is linearly independent or not. So what should be the answer? Check it quickly. What is the answer? And what should be the answer? Without checking, just tell me what should be the answer. Without checking the Wronskian, just tell me what should be the answer. It should be linearly dependent or independent. How many people are preparing for the GATE?
Dependent, sir.
Dependent. Okay, you can also check that without checking the Wronskian. You can also check that. You can write it like this: cos 2x equal to what?
Cos 2x, sir, can be written as
Cos square x
minus
minus
sin
sin
square x by
square
2.
x. Okay, then you can see that cos 2x 1, right? Here just move it. You can see that those coefficients are not 0. So C1 equal to 1, C2 equal to 1 and C3 equal to minus 1. What does it mean? Linearly independent. But the thing is, you know the formula. That's why you are able to do that. What if we have some another situations? You cannot do like this. Okay? So the best part is you have to do like this. So cos 2x cos square x sin square x. Now what is this? 2 sin 2x, and this is what? Minus 2. This is exactly minus sin 2x, and this is what? Sin 2x. Are you getting why I have written sin minus sin 2x and sin 2x? Because this row is the first derivative. Is it fine?
Yeah, fine, sir.
And this one is what? Minus 4 cos 2x. And this one is what? Minus 2 cos 2x. And this one is what? 2 cos 2x. Okay? Now find the derivative. I mean, not derivative, determinant. What you will get? Cos 2x. And this one, that is minus 2 cos 2x and sin 2x, that is another sin 4x, and this one is what? Plus again sin 4x minus cos square x. Similarly sin 4x sin 4x plus sin square x. Similarly sin 4x minus sin 4x, and all terms are 0. So that's why Wronskian here is 0. So the S is linearly independent. I know that this way is lengthy, but what if we don't have such formula? They just give you some logarithmic formula. Then how we will do that? Okay, so that's why. And when you solve some differential equation, linear differential equation, then you will get some kind of Wronskians. So that thing we will talk about it. Okay, so for now just know what is Wronskian. Okay, so let's talk about vector spaces.
Sir, linearly dependent.
Oh sorry, linearly dependent. Okay, vector spaces. Are you guys interested to learn this? What is vector spaces?
Yes, sir, yes.
Yeah, okay. So let V, capital V be an arbitrary non-empty set of vectors on which two operations First one is addition and multiplication. Okay, are defined by. Okay, now I will talk about the axioms. So axiom number 1, if u and v belongs to vector capital V, then u plus v must also be an element of capital V. So that is the first axiom. Now the second axiom, u plus v must be exactly equal to v plus u, and that should also be an element of vector V, vector space. Okay, so here I am talking about capital V. If V is a vector space, if this V, capital V is a vector space, then all these axioms should be valid. Okay, now the third axiom is u plus v plus w is equal to u plus v plus w, and all u v w must belongs to capital V. If this is applied, then also we can say, I mean all should be applied, not just one. All these are conditioned to have vector space. And now the fourth situation is, there must exist zero element in V such that 0 plus u must also be equal to u plus 0 equal to u. This is the fourth axiom. Now the fifth axiom, it says, for each u belongs to V, for each u, then there exists minus u in V such that u plus minus u must equal to 0. This is the fifth axiom. Now the sixth axiom is, if k belongs to real number, belongs to the set of real number, and u belongs to capital V, then it is saying k times u must also belong to capital V. Okay, now the seventh axiom, k times, I am talking about this k, that is all set of real number. So k times u plus v must be equal to k times u plus k times v. Eighth, it is saying k1 plus k2, and k1 k2 is what? Set of real number. k1 k2 times u must be equal to k1 u plus k2 u. 9. This is the last axiom. K times u times v, if it is like that, no, not, you cannot write like this. This is another set. K1 times k2 times u, that must be equal to k1 k2 and u. So to have set V to be vector space, all these axioms must be applied. Now there is one more, I forgot that. There should be, if you multiply identity must also be a belong to vector V. So if you multiply identity times u, that should also be equal to u. The total 10 axioms. Is it fine? So
Yes, sir.
yeah, so for any set V or for any space V, if these 10 axioms applied on that, then that set V is called what? Vector space. Let's say take an example. Is n-dimensional space a vector space? Tell me. Is n-dimensional space? N-dimensional space means what? You have the set U such that it has n number of elements of all real numbers. So that is what? N-dimensional space. And here U is not fixed. All entries are what? Any kind of real numbers, and those kind of real numbers should be n. So that is called what? N-dimensional real space. Now it is saying that is n-dimensional real space a vector space? That is the question. Just think about it. To do that, first check it. Now just take it any element from n-dimensional space, u and v. Okay, so definitely u and v, any kind of n-dimensional vector u and v will belongs to the n-dimensional space. Now just add it, u plus v. Can that belong to Rn? Will that belong to n-dimensional space? If you add it, will that belong to the n-dimensional space? Yes or no? Just take any kind of u and v from n-dimensional space. Now add them. Will that belong to the n-dimensional space?
Yes.
Yes. So first axiom done. Now second axiom. Will u plus v is exactly equal to v plus u? That is also true. Now take u times, not times, u plus v plus w. This is also true. U plus v plus w. I mean, I want to say from number 1 to 3, all these three axioms are done, right? Now there is a turn of fourth axiom. Can zero vector also exist in n-dimensional space? Zero. Fourth axiom is what? Fourth axiom is there must exist zero vector in V such that 0 plus u equal to u plus 0 equal to u. Will that zero vector exist in n-dimensional space? Respond guys, otherwise we cannot complete it.
Yes.
Yes.
sir.
Yeah. 0 will also be an element of n-dimensional space. Fourth axiom is also done. Can exist minus u in n-dimensional space? That is also true, because here all those entries are real numbers. So if you have some entries in u like this 1 1 1 1, then definitely minus 1 minus 1 minus 1 is also that the part of n-dimensional space. You can take any kind of u in Rn, you will always get minus u from Rn, because that Rn is what? N-dimensional real space, and all those scalars are real numbers. There is no such restriction to get that. So which means that for every u, you will have minus u. So the fifth axiom is also done. Fine. Now the turn is sixth.
Yes, sir.
Sixth is also done. If you multiply any u by scalar, you will get another vector, and that is also part of n-dimensional space. So you can see that all those 1 to 9 axioms all are valid. So which means that what? Rn is vector space. Fine?
Yeah, fine, sir.
Now let's take another example. Let the operation for u v belongs to vector, and that is nothing but the two-dimensional vector space, and k is a scalar that is belongs to real number, and that operation is defined as u plus v equal to u1 plus v1 comma u2 plus v2, and second operation is k times u equal to k times u1 comma 0, which means that you can take any kind of u or v from the second dimensional vector space. I'm not saying this is a vector space now, but v is a set that is second dimensional. I mean, all those u and v are like this. Okay, now the operation is, if you take any two vectors u plus b, that operation will be like this, and if you multiply any scalar in u, that operation is like this. Now the question is v a vector space?
Yes, sir.
Anyone else? Okay, you can see that all those operations on addition, that is valid. If you take any kind of u plus v, you will get this, and if you do v plus u, you'll also get the same. So any kind of addition operation is done here. Addition axioms are check. Now let's take multiplication operation. Suppose I will take an scalar u, okay, and I will multiply with u, and from that operation, and suppose u is like this, u is something like u1 and u2, because you can see that whatever I have take v, that is R2 space, that is I will have two elements, u1 and u2. Now it is saying that if you multiply u with k, you will get it like k u1 comma 0. Fine. Now the thing is, it is saying that you can take any kind of u, you will always get this only. Where is u2 then? Where is u2 then?
No, sir. No, sir.
Whatever you are multiplying scalar with u, you will always get k u1. which means that those vectors where the components are u1 and u2 like that, then that vector is not mapped here. That is not the part of that axiom, which means that multiplication operation is not valid. Is it fine? Then V is not a vector space. Okay, now suppose if it has given like this ku1 and ku2, then it was fine. But directly it is saying that there is no such term of u or u2, which means that then what happened to the u2? Which means whatever you will multiply k times u, then that component will be just ku1 and 0. Then what happened to those vectors which are part of V? So that's why this is not a vector space. Fine? Any problem here? A matrix M by N. A set of matrix of order M by N. Is it a vector space?
Yes.
Yes. Okay, fine. Now I think you understood. Any problem here? How it is vector space?
So, the vector space can have multiple dimensions.
Yeah, any kind of dimension. Any kind of dimension. Vector V belongs to n dimensional space. Okay, fine. Any kind of dimension it have.
Yes.
Okay, now let's move to the subspace. What is subspace? You know, I can talk about it, the vector space, the whole year, whole months. It will not finish. But the thing is, you have to, read books. Then you will get it. I don't have much time for that. So that's why I am moving forward. Now, what is
Sir,
subspace? Yeah, tell me.
Can you suggest some books for this text part?
Yeah, you can easily get one. I mean, for engineering purpose, you can get, you can read this book, Gilbert and Strang. Have you heard it? Gilbert and Strang. Okay. Oh man. This is one book.
And for GATE?
Forget, you don't require it. Forget, there is no such syllabus. Just eigenvalue, eigenvector, linearly dependent, independent, rank. That's it. They don't ask so much things. Okay? Yeah. There is one more book. If you want to get into more theories, there is one more book, Friedberg. So these books are, this book is for engineering applications. Engineering applications. But this is more or less very theoretical. You will not get matrices. But the thing is, you know what? The beauty of the linear algebra is you will not deal with the matrices. Matrix is a part of that. Matrix is another space. What I talked about that. In that Wronskian, I am talking about the functions. Where is the matrix? There is no such matrix. Okay? So when you go into the more mathematics, then matrix will go. You will not talk about the matrices. Okay, so let's talk about the subspace.
The tensors are included in the.
Tensor is a very general thing. Every linear algebra concept is inside the tensor. Tensor always follows the linear transformation rule. Okay, the thing is, let's see. This is the tensor. Okay, inside it, linear algebra, and inside it, matrices, and inside it, vectors, inside it, scalars. So like that. Okay, so I will not talk about, I will talk about it later. Okay, so I will just remove it. Okay, let's talk about subspaces. What is subspace? It is actually, it is already saying subsp means subset. Okay, a subset W, it's not Wronskian, W of a vector space V is called a subspace. A subspace of V if W itself a vector space. Okay, are you getting what it is saying? It is saying that suppose you have a vector space V. Okay, now take some elements from that or subset of that. If that subset is alone a vector space, then that subset will be called what? Subspace. Okay, the thing is, if you have a vector space V, it doesn't mean that if you take some subset from that, it doesn't mean that that subset will always be a vector space. But if it is a vector space, then that subset is called what? Subspace. It's fine? It's fine or not?
Yes, sir.
Okay, so let's take an example. Let W be any plane through origin. Is it a subspace? In linear algebra, you have to apply your intuitions. Sometimes, you always know that this thing is true, but it's very difficult to prove it.
Yes, sir. It's a subset.
So that is the very difficult part. So there, research and mathematicians comes into the picture. They already know that. They already know that this is always true. But the thing is, to prove this, it's very difficult. But I will not go into the proving things. Sometimes I will prove this, some very important concept I will prove this, but not always. So this is the question.
Yes, sir. It's a subset.
Is it a subspace?
Yes, sir.
Yes. How? Just explain this. I don't need proof. Just explain this how.
Because it's a plane, it can pass through the origin.
I mean, you have the set of planes. Suppose you have the set of planes like this. The plane which are passing through the origin, you have like this, right? Fine?
Yes.
And this plane is passing through the point like this. Suppose u equal to x1, x2, x3. Now take another point v, that is y1, y2 and y3. Now you can see that if we do u plus v, then what will happen? x1 plus y1 plus b, x2 plus y2 plus c, x3 plus y3. Fine. Now separate this. You will get plane 1 plus plane 2 equal to 0. Not equating to 0, just check it whether it is a 0 or not. You can see that this is nothing but the p1 plus p2 equal to 0. And what is p1? P1 is nothing but a x1 plus b x2 plus c x3 equal to 0. And what is p2? A y1 plus b y2 and c y3 equal to 0. Now you can see that it is completely satisfying. Similarly, take c times u. You will get like this: c times p1, and what it is 0. So every time all vector space axiom will satisfy. We can also think like this: such a plane that is passing through origin. Let's take one point that is passing through the origin. That is suppose ki u, and another is what? V. And the vector sum of u plus v is what? That is also passing through the origin. C times u is what? That is also passing through the origin. So that's why it is always clearing all those axioms. That's why all those set of planes which are passing through the origin is subspace. Is it fine? And what about lines passing through the origin? Let's take a line. It is also a subspace. Is there any problem here? If plane is subspace, then line is also a subspace. Any problem?
No, sir.
Okay, let's move to another theorem. If ax equal to 0 is a homogeneous linear system, of m equations with n unknowns, then the set of solutions vectors is a subspace of n-dimensional real space. It's fine. Let's prove this. What it is saying is, you have the system of homogeneous system of linear equation Ax equal to 0. Now it is saying that all the solution set will form a subspace. What is the requirement of subspace? Suppose x1 and x2 is a part of solution. Okay, then what it is saying is, if you take ax1 plus x2, then that must be equal to what? Ax2 plus ax1. Then you can see that that is nothing but ax2 plus ax1. That is also a 0. Fine. Is it fine or not? Now take another solution like this, k times x1. So what does it mean? If you satisfied kx1, then what does it mean? Which means that k times ax1, that is also a 0. That is also part of the solution. Now it is saying that 0 vector must be the part of the solution. You can see that if A is non-singular, if A is singular, then which means that trivial solution is also a part of that. What it is saying is, if x1 exists, if x1 is the solution of this, then minus x1 must also be the solution of that. That is also a part of the solution. So which means that what? It is a subspace. Fine. Now it's getting boring, right? Tell me.
So not boring, but overloaded. Sir.
It's interesting.
Yes, sir.
Okay, good then. Are you getting what I'm trying to say?
Sir.
Don't worry, I will upload on my YouTube channel and repeat it. Then you will get. Okay. Now let's move to the spanning the space. That lady asked me some days ago that what is the spanning the space. Are you here?
Yes, sir.
Yeah. Spanning a space. Okay. So what it is saying is, if set is like this, u1, not u1, v1, v1, v2, vr is a set of vectors in vector space V, then W of V consisting of the set of all linear combination of S is called space spanned by S, or you can also write W equal to span of S, or W equal to span of set V1, V2 and VR. Just read it and try to get it. What it is saying is, from vector space V, and that vector space will what? n-dimensional real space. From the vector space V, just take R vectors out of that. Okay. Now from that set, you have to create W set such that all linear combinations are possible. W is nothing but all kind of linear combinations. Then that W will be called what? The space spanned by this. For example, if you have three sets like this, E1 equal to 1, 0, 0, E2 equal to 0, 1, 0, and E3 equal to 0, 0, 1. If you take the span, of these three vectors, which means that if S is like this, E1, E2, and E3, then what is the possible linear combination of W? That is called three-dimensional real space, right? Exactly equal to three-dimensional real space. If you take any kind of linear combination, that will be exactly equal to three-dimensional real space. Is it fine or not?
Yes, sir.
So that is the definition of spanning the space. Spanning the space means nothing but just take the all possible kind of linear combination, and that set is called spanning the space of that set. That is the definition of spanning a space. And this space is nothing but this. And the span of S is what? W. It's fine?
Yes, sir.
Yeah. Now let's move to the what is basis and dimension. It is saying if V is any vector space and S is a set of some vectors v1, v2 dot dot vr in V, I mean this one belongs to V, then S is called a basis for V if first condition S is linearly independent. B, S span V. It's fine. It is saying that from vector space, just take some elements v1, v2, v3, vr, and that set will be called as a basis for V if all those sets are linearly independent. And also that S must span V, which means that if you take all kind of linear combination, that must span V. It is exactly this previous example. You can see that all these three vectors are the part of three-dimensional vector space, right? Now what I am saying is just take three vectors E1, E2 and E3. So we can call E1, E2 and E3 is a basis for vector space if these three are independent. That is the first condition. So which means that for three-dimensional space, we can call these three vectors a basis. This is one of the basis. I'm not saying that this is only the basis. This is one of a kind of basis. The thing is, these three are linearly independent. That's why it is also a basis. But the thing is, this is not only the basis. Now the second condition, it is saying S must span V. What it is saying is take all the linear combination of these three and that should span V. That is also true. It's fine or not?
Yes.
Is it okay for you, lady?
Yes, sir.
Okay, now the thing is, then what is coordinates? What is coordinate? We always talk about, right? What is coordinate? Suppose we have for three-dimensional space. Let's take an example for three-dimensional space. We know that one of the bases is this 1 0 0, E2 is 0 1 0 and E3 is 0 0 1. Now someone asked, will I get the vector 3 2 1 from this basis? I want to say that if all kind of linear combinations, since these three are linearly independent, which means that I can get this vector by some linear combination of these three.
Yes, sir.
So which means that yes, I can write it, take like this. So which means that this vector, B can be written as CE1 plus CE2 plus C2E2 and C3E3, and this C1, C2 and C3 is called what? Coordinate. But there is a catch. The catch is this coordinate is only for the basis of this. But there are many possibilities. What if I have the basis this? And I want to get the vector B, the same vector. Will that coordinate be same?
No, sir.
Why? Because here
Since
basis
it
is
was-
different. So which means that whatever we earlier were talking about the coordinate, those coordinates are always based on the rectilinear, not rectilinear, rectangular basis only. But there are lots of basis possibilities. For this basis, coordinates are different. You can see that I can write like this. And for this time, you can check that you will get coordinate is like this. From high school, if someone asks if you have the vector, position vector 3 to 1, then what is the coordinate? Then people will blindly say coordinate is 3 to 1. But if you are intelligent, if you understand the linear algebra, then suddenly you will ask for which basis you are talking about.
Sir, for for the coordinate there can be infinite possible bases.
Yes, but the number will be only 3. Fine. The number will be only 3. There will be infinite number of possibilities, but the number will be always 3. The number of those basis vectors will be always 3 for 3-dimensional space I am talking about. And what about 4-dimensional space? What will be the number of bases? It is 4. For 5-dimensional it should be 5. Fine.
Yes, sir.
Yes. So then another theorem came. Let set v1, v2, vn be any basis from V. Then the first is if a set has more than n vectors, then it is what it is, linearly independent or dependent? Tell me. First, what it should be?
Dependent.
Great. It should be dependent. If it is more than n, okay, and if it has fewer number than n, then definitely that will not span the whole vector space. That is also correct. Okay. Now let's talk about the dimension. What is dimension then? A finite dimensional vector space V, that is also called dimension of V, is equal to number of vectors. Vectors of what? Again, I will write it again. Sentence is not correct. Dimension of V equal to the number of vectors in where? Basis. It's fine. So if someone asks what is the dimension of that vector space, that is nothing but the number of vectors in basis, that basis. Which means that if you talk about three-dimensional space, then what is the dimension? It is always says three-dimensional. What does it mean? We have only three bases. Four-dimensional. What is the dimension? It always says 4, because the number of possibilities of bases is what? 4. For two-dimensional, 2. So the dimension of vector space is nothing but the number of vectors in its basis. So that is called dimension. Fine?
Yes, sir.
Okay. Can I ask one question? This lecture is going, very extensive. It will take time. I will talk about 14 minutes more. It's fine or not?
Yes, sir.
Yeah. So now let's take one question. Determine a basis and dimension of the solution space. You have to make efforts, because you guys don't make any efforts in solving the problems. Just you guys are just listen it, but you have to make the effort, otherwise you cannot understand. It is asking find the basis and dimension of the solution space. First, just tell me what is the number of solutions. After just looking, what will be the number of solution of this system?
So infinite.
Infinite. Good. Now solve this and find the dimension and basis of that solution set. Okay. So after solving, you will get it x1 equal to minus s minus t, x2 equal to s, x3 equal to minus t, x4 equal to 0, x5 equal to t. Now write it in the vector form: x1, x2, x3, x4 and x5. So I can write it minus s minus t, s minus t, 0, t. Now take s here plus t here. What will be the entry here? what will be the entry?
2.
How much?
-1.
Minus 1, minus 1, 1, 0, 0, minus 1, 0 and 1. Now you can see that you have only two bases. What is the basis? The set this. Just write B1. Minus 1, 1, 0, 0. And second basis is what? Minus 1, 0, minus 1 and 1. And what is the dimension? 2. Fine. Because here the solution set is like this. You have to just vary S and T and you will get all the solutions. So what did I do is I have just separated, which means that all solutions are the linear combination of these two, which means that what? This is the basis. Fine. And the number of bases is equal to what? Dimension of that solution space. I mean, in this case it is solution space. Fine.
Yes, sir.
Now let's talk about
Yes, sir.
row space. What is row space? Not just row space, column space, null space. Okay, so let's take a matrix that is A11, A12, A1n, and that matrix is of the order m by n. So A21, A22, A2n. Now A m1, A m2, that is A mn. Now from the definition, the first row I can write it like A11, A12 dot dot A1n. Second row is what? A21 dot 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 A2n. Similarly, mth row we can write it A m1, A m2, A mn. Okay. Similarly, if I can write column 1, that is A11, A21, A m1, and column 2, that is A12, A22, A32, like this. Okay, and nth column A1n, A2n, A mn. So from the definition, row space is nothing but the subspace of Rn. Note that it is Rn. It is talking about Rn 1, 2, 3 up to n. Subspace Rn spanned by the row vectors. Okay, this is called row space. Now column space. The same thing, the subspace of Rm. Okay, because it is talking about what? Columns. It is m dimensional. But row, it is what? N dimensional. Okay, so that's why the subspace of n dimensional real space by columns of subspace spanned by. Fine. Now what is null space? Null space, it is saying the solution space of the homogeneous system of linear equation Ax equal to 0. Okay, so in the null space it is saying the solution space of the homogeneous system of linear equation Ax equal to 0. So from that definition it is saying it is the subspace of Rn, because whatever you get the solution, that is the number of columns, because there are n number of unknowns. It is the subspace of n dimensional space is called null space. It's fine?
Yes, sir.
Are you getting it?
Yes, sir.
Yeah. Now let's talk about the rank and nullity. Should I talk about it or finish it? Rank and nullity. Should I complete it or should I talk about in next lecture?
So complete it.
Complete it. Okay, great. Okay, now let's talk about rank and nullity. First theorem, it is saying the dimension of row space of A exactly equal to dimension of column space of A. Whatever you get, the dimension of the row space of A is exactly equal to the column space of A. Now C is dimension of null space of A. A exactly equal to, it is called nullity. C, rank, now it is point. Rank of A equal to rank of A transpose. And also here I forgot, dimension of row space of A equal to dimension of column space of A, that is also equal to rank of A. Okay, now the dimension of null space of A equal to nullity, and the third one is the rank of A is also equal to rank of A transpose. Now the fourth point is that this point is very important. Rank of A plus nullity of A equal to n. This is called rank nullity theorem. What is happening? Yes. So it is saying that if you have the number of bases for the row space of A, the dimension is exactly equal to the column space of A, and that is also equal to the rank. That is called rank. Now the dimension of null space of A, whatever you got, that is exactly equal to the nullity. And now the thing is, what is the nullity? If you have n dimensional space, or for the system Ax equal to 0, then what is the n? N equal to the number of unknowns. That was the number of unknowns, right? So you can see that the nullity of A is exactly equal to the n minus rank of A. And if you are remembering, then we already talked about that rank of A is exactly equal to the number of leading, are you recalling it, leading variables of row reduced echelon form or row echelon form, which means that the nullity is nothing but the number of free variables are you recalling it? What I'm trying to say is, suppose you had the matrix m by n, okay, now you are getting RREF like this and all elements are zeros. So what I'm trying to say is, suppose it is a m by n, so which means that there will be n columns and m rows. So which means that this number, whatever it is, this is the rank, and whatever you left, and that is nothing but the n minus r, that is called nullity. Are you getting what I'm trying to say? The number of free variables is called what? Nullity. Are you getting?
Yes, sir.
So we have the table. Space dimension, which means that row space of A has dimension R, column space of A, what is the dimension of column space? If row space of A has the dimension R, then what is the dimension of column space of A? Tell me. Tell me.
R.
Only.
Yes, only R. And what is the null space of A? If R is the dimension of the column space or row space of A, then what is the null space of A? What is the dimension of the null space of A?
N minus R.
N minus R. And what is the null space of A transpose?
It would be same.
No, it will be M minus R. Just transpose it, then get the solution. Then the number of columns will become the number of rows.
Rows.
Okay, and the dimension will remain same whether it is A or A transpose. We have already talked about that. So this time the null space will be what? M minus R. Okay. Okay. So now there is another thing. If M is greater than N, then rank of A will be what? This or this? It should be N.
Less than equal to.
Yes. Or you can also say that less than or equal to minimum of M comma N. Whatever the minimum is, the rank will be either exactly or less than that. So that is the another important thing. Okay, so now After completing this, we can get we can summarize the nature of the solution. Nature of solution. First, if it is in the form of ax equal to b, then it will have two conditions. First condition is either it will be consistent or it will be inconsistent. If it is consistent, then it will have two more conditions inside it. The first condition is if rank, consistent means what? Solution will exist. Inconsistent means no solution. Okay, if rank of A equal to rank of augmented matrix is also equal to n, then it will have unique solution. And if rank of A equal to rank of augmented matrix A is to B equal to same but less than the number of variables, here the number of variables, then it will have infinite number of solution. And in the case of inconsistent, there will be always the rank of A is not equal to rank of A is to B. This is the first case if it is inhomogeneous. Now the second, if it is like this, homogeneous, then what will happen? Will it always be consistent if it is homogeneous? If it is homogeneous, will it always be a consistent? Tell me.
Yes, sir. Yes, sir.
Yes, it is always consistent. You will always get the solution. Either it will be it will always a condition. The thing is, it will have only one condition, two condition. One, it is a trivial, or another it is a non-trivial. When it is trivial, if rank of A equal to the number of variables. When it is non-trivial, when rank of A is less than number of variables. This is the condition. Whatever I have explained earlier, you will have good ideas what could be the reason of these two. Okay, and also I have attached some previous year gate problems you can solve by using all those theorems. Okay, I have attached 3 problems and you can
Sir.
easily solve it. Yeah.
Sir, this OneNote is synchronized with the YouTube channel.
Yeah, what YouTube channel?
The link you have shared in the previous sessions.
Yes.
The OneNote is synchronized with the.
Yes,
with
yes,
account?
I have already whatever, because yeah, I have solved, I have shared with the link. So whoever has that link, they will have updated version.